For this worksheet, we're going to use Hooke's law to calculate the force of the spring and then the period of the spring equation as well. We've got a setup where in position A, there's no mass attached to the spring, so the spring is at its equilibrium. Position B, we've got mg hanging. In position C, we have 2 mg hanging. What force is causing the spring to extend during experiment B and C? Well, in experiment B and C, we've got a mass pulling down on the spring, and the reason that mass is pulling down is because of the force of gravity. So nothing crazy here, it's just simply the force of gravity pulling down on the spring. What is the total extension of spring A? Explain your answer. Well, spring A is not extended. It is where it wants to be. It's in its happy place. It's at the spring's equilibrium. At this point, the spring is the entire system, but there's no mg pulling down because we'll consider the spring to have 0 mass. And the spring's not pulling up because the spring is at its equilibrium. So the answer being filled in is 0 meters. There is no mass attached, therefore no force of gravity. Derive a formula to calculate the spring constant K of spring B in terms of m, g, and x. Well, if the system's at equilibrium, we have balanced forces. Pulling down is mg. Pulling up is the force of the spring, negative kx. So we're just going to set this up based on that equilibrium. Force of spring is equal to force of gravity. Because it's at equilibrium, we have those balanced forces. If Fg is equal to Fs, mg would be equal to negative kx. Now, we don't really use that negative very often. The negative just indicates it's a restoring force. If it's displaced to the right, the restoring force is to the left. If the displacement is down, the restoring force is up. So while I'll put the negative in, don't get hung up on the negative. It just means it's restoring. You don't really use it in the calculations. Fg is equal to Fx. Mg is equal to kx. Divide the x over, and you get k, the spring constant, is equal to mg over x. If the hanging mass weighs 50 newtons, remember that's the force of gravity. That's not the mass. As a result, the spring is extended 0.2 meters. That is your x, your displacement. Calculate the spring constant of B. From our formula above, we have 50 divided by 0.2. And then 50 divided by 0.2 should get us 250. As our spring constant. Neither B nor C are currently experiencing a higher restoring force. Both of them at this moment in time are in their own equilibrium. Yes, C is being pulled down much further. Yes, the force of spring is greater on C than B, but the force of gravity is greater on C than B. The restoring force is the net force. In this case, on a vertical spring, the restoring force is the net force between gravity and the force of the spring. In B and C, they're both at equilibrium. If they are both at equilibrium, neither one of them has a greater restoring force than the other. Both systems are at equilibrium. Both systems have balanced forces. Both of them have a net force of 0. All right, we've got a horizontal spring. Position A is at equilibrium. B is at amplitude to the left. C is at amplitude to the right. Amplitude being the farthest displacement from equilibrium. And we need to check the correct boxes for each location in regards to velocity and acceleration. So at equilibrium, we're at maximum velocity, 0 acceleration. At position B, we've got 0 velocity and maximum acceleration, just like at position C, because B and C are both at amplitude. So again, velocity 0, acceleration at maximum. To explain our answer, there's a couple of ways we can look at this and to explain it out. Acceleration is caused by the restoring force of the spring. Restoring force pushes an object back towards the equilibrium. At A, it is at equilibrium, so no restoring force or acceleration. However, at this point, it also has maximum speed. Meanwhile, at B and C, the block is at maximum displacement from equilibrium, so it has a maximum amount of restoring force and acceleration. It's also changing direction, so velocity equals 0 for that small moment in time. So I'm just writing this out as position B and C represent the amplitude. This is the farthest from the equilibrium. If it's the furthest from the equilibrium, we have the maximum restoring force, and maximum force means maximum acceleration pointed back towards the equilibrium. At amplitude, that's where it changes directions. And when you change directions, you have to go through velocity of 0. So for a very small moment in time, it has stopped. At position A, you're at equilibrium. The restoring force would be 0. And the reason the restoring force is 0 is because you are where the system wants to be, equilibrium. You have been accelerating or speeding up until you got to that position, so that will be your maximum velocity. And as soon as you pass that position, your velocity will begin to slow down as it eventually turns around at amplitude. Consider the object oscillating above. If the mass of the object is 5 kilograms and the spring constant is 25 newtons over meters, what will the period of the oscillation be? Well, the period of a spring is calculated as 2 pi times the square root of mass attached to the spring divided by spring constant. In this case, that would be 2 times pi times the square root of 5 divided by 25. So in our calculator, we'll take 5 divided by 25, which I think will be 0.2. We'll square it, then we multiply by 2 and multiply by pi. That will get us the period of this spring. .81 seconds. Remember, the period is the number of seconds it takes to complete one oscillation. So the unit for the period is in seconds. If the mass of the object is 12 kilograms and the spring was 240 newtons over meters, what will be the period of the oscillation? So 2 pi times the square root of 12 divided by 240. Again, we'll take 12, divide by 240 in our calculator. We'll square root that value and then multiply by 2 times pi. And we get 1.40 seconds because that's the unit of period. For the last question, a 40 kilogram object has a period of oscillation of 1.25 seconds. What's the spring constant? A little bit different now. They've given us the period of 1.25 is equal to 2 pi times the square root of 40 divided by k. We'll take the 1.25, divide by 2, divide by pi. If you want to divide by 2 pi, make sure you put it in parentheses. Otherwise, your calculator will think you're dividing by 2 and then multiply by pi. So just be careful. Divide by 2, then divide by pi, then square both sides. You get about 0.04 is equal to 40 over k. Now, I am rounding, and I'll keep my decimal places on my calculator. So I'm writing out 0.04 is equal to 40 divided by k. The 0.04 and the k change places, so it's 40 divided by 0.04. But if you leave all of your decimal places in your calculator, you get 1010.65.